particle motion. We're going to be talking about some kind of particle moving. And in calculus, we really discuss the movement of these particles on either the x or the y-axis. So we're talking about horizontal or vertical motion. At the time, we're just going to stick to horizontal motion. So we're thinking about this thing going back and forth along the horizontal axis. So we need to think about what that means when we talk about velocity and acceleration. So let's write down some definitions. Let's suppose that P of t is a function defining the position, P for position, of a moving object at some time t. So it's going to give us this position along the x-axis. Well, what does that mean about average velocity? The average velocity is really the average rate of change of position. So it's this change in position over the change in time. Easy, that would be P of B minus P of A. So the position at the end minus the position at the beginning over the change in time. Change in position over the change in time. Let's compare that to instantaneous. Now, instantaneous velocity is the velocity at a specific time, not over a period of time. So average velocity is over a period of time. Instantaneous is at a singular time. So that's going to be the derivative of our position. So we have to be very careful on whether it's asking for average or instantaneous velocity. So let's take this one. We have a particle's position, P of t equals e to the t sine t. P of t is measured in centimeters and t is in seconds. What is the average velocity on the interval from 1 to 3? So we would want to know the position at 3 minus the position at 1 over the change in time, change in position over the change in time. So for this one, let's go ahead and use our calculator. So what I would do if I was going to be doing this problem in my calculator is put the function in y1. So e to the x in our calculator times the sine of x. And I'm just going to make sure in my mode that I am in radians. Good. So we want that function evaluated at 3 minus that function evaluated at 1. So I'm going to go ahead and set up a fraction and do alpha f4 y1 of 3 minus y1 at 1 over the change in time. And I get 0.274 because we want to go 3 decimal places. And it said to make sure we use the right units. So the difference in our position was in centimeters, over the change in time, and that was in seconds. Instantaneous velocity. instant. That's going to be the derivative of our position. Now remember, our position function is e to the t sine t. So to find the velocity at a particular time, we're going to take the derivative of position. Well, this one's pretty easy to take the derivative of. Derivative of the first would just be e to the t times 1 times sine t plus the first function times the derivative of the second. And then if we evaluate that at 1.5, I'm going to get, and we want the derivative with respect to x of y1 evaluated at 1.5. 4.787. Centimeters per second. Now I want to make sure we notice something here. When we had just a function, f of x, and we're talking about the slope of the secant line. The secant line meant it went through 2 points. The slope of the secant line would have been the function, change in y, over the change in x. Slope of tangent line would have been the derivative at some point. Notice how that's very similar to average velocity, average rate of change, and this is instantaneous rate of change, or in our case, instantaneous velocity. So what does this mean about acceleration? Well, acceleration is our change in velocity. So let's remember, p of t is position, p prime is velocity, so what would be acceleration? Well, it depends on if we're looking for the average acceleration over a period of time or instantaneous acceleration. Average acceleration would be the velocity, change in velocity over the change in time. Instantaneous acceleration would be the derivative of velocity at a particular time, which means that it's the second derivative of position. So, continuing with the same function we had earlier, e to the t sine t, let's talk about acceleration. So we already knew what the velocity function would be. That's the derivative of position, and we found that to be e to the t sine t plus e to the t cosine t. So what would be average acceleration? Well, average acceleration would be the velocity at the end time minus the velocity at time 1 over the change in time. Which, if we go to the calculator, so what I'm going to do is I'm going to do the derivative of our position at 3, the derivative of our position at 1, and now I'm going to take the derivative at, so the velocity at 3 minus the velocity at 1 divided by that change in time. And I get negative 10.403. Now, what would be the units? So velocity was centimeters per second. So acceleration is centimeters per second squared. Centimeters per second per second. Because this was centimeters per second, and then we're dividing by seconds. So that's why we end up with seconds squared. So instantaneous acceleration. Well, we have our velocity function, which was the derivative of position. And if I wanted to find instantaneous acceleration, I'm going to take the derivative of velocity, which would give me derivative of the first times the second plus the first times the derivative of the second plus, now I'll take the derivative of this term, derivative of the first times the second plus the first times the derivative of the second. And if I wanted to find that instantaneous acceleration at 1.5, I'm going to be plugging in 1.5 for all the t's. Cosine 1.5 minus, and I got 0.634. And again, this would be centimeters per second squared. So let's kind of summarize this. When we were talking about functions, our basic function, basic graph was f of x. When we're talking about particle motion, that corresponds with our position. The derivative of f is going to correspond with the derivative of position, which means velocity. Oops. The second derivative of a function, in our case, that'd be the second derivative of position, which is the derivative of velocity, which is acceleration. So if velocity is 0, That means our first derivative is 0 or undefined. What is happening with the position when we have velocity of 0? Well, what's going to be happening is we're going to have a potential change in direction. What if velocity is greater than 0? What is that going to mean? Well, that means position is increasing. And if we're talking about a particle moving horizontally, that's going to mean that the object is moving to the right. Increasing movement. Negative velocity, position is decreasing. So our object or particle is moving to the left. If our velocity changes from positive to negative, that means the object was moving to the right and now is moving to the left. So I'll say particle, object, whatever we want to call it, changes from moving right to moving left. If velocity changes from negative to positive, well, that means the particle changes from moving left to moving right. Acceleration. If acceleration is 0 or undefined, that's going to be a potential change in sign of velocity. If acceleration is positive, then velocity is increasing. If acceleration is negative, velocity is decreasing. If acceleration changes from positive to negative, then velocity changes from increasing to decreasing. And if it's changing from negative to positive, we'll reverse this. Changes from decreasing to increasing. Now let's look at a graph of particle motion. So we have a graph of particle motion. Now note that the particle's not moving up and down, it's moving left and right. At which point is the velocity equal to 0? Remember, velocity is the derivative of position. So when is the derivative of the position 0? Well, that's happening at B and D. Why? Oh, they called this one S of t. S of t changes, oh, I should have said because. S of t changes direction. At which point does acceleration equal 0? Well, that would be the second derivative. That's going to be a point of inflection. That's happening at C. S of t has a point of inflection. On what intervals is the particle velocity positive? Velocity being positive means that our position is increasing. So this being positive means position is increasing. So that would be here to here. And D on. Now note I started at time 0 because time usually starts at 0. Velocity is negative. That means that position is decreasing. Well, that happens from B to D. Let's note also what these also mean. If position is increasing, we're moving right. If position is decreasing, the particle is moving left. When is the particle's acceleration positive? Well, that's the second derivative, so we're looking for concave up. So what interval is this graph concave up? Well, that starts at C and all the rest of the graph. So on C to infinity. When is acceleration negative? Well, that happens when we're concave down, which is going to be negative infinity to C. Five commandments of particle motion, specifically for horizontal movement. If the velocity is positive, the object is moving to the right. If velocity is negative, the object is moving left. Now, sometimes we're talking about speed. So I want us to think about when would our speed be increasing? When is the particle speeding up? Well, that's going to be happening when velocity and acceleration have the same sign. The speed is decreasing when, I guess I didn't need a comma there, when velocity and acceleration have opposite signs. The last rule: if velocity equals 0, but acceleration does not equal 0, this means that the object momentarily, I cannot spell momentarily, stops and changes direction. What would it mean if both of them were 0? Velocity is 0 and acceleration is 0. That means we stopped completely. Okay, last example. Feel free to work it out and then just fast forward and check your answer, or join me. Find the values of v of 3. So we have a function, v of 3, so we're given the velocity. It's going to be 3 plus 2 times 3 plus 4 squared, which this is 5. That's 7 squared is 49. And then 5 times 49 is 245. What would be the units? Well, t is in minutes. Velocity is inches per minute. So this is inches per minute. V prime of 3. Well, we would need v prime, right? So let's think about what that would be. So v prime, let me use the product rule, right? V prime of t would be the derivative of the first times the second plus the first times the derivative of the second, which would be 2 times t plus 4 to the 1 times the derivative of the inside, which is 1. So if I'm plugging in 3 to that, that's going to be 3 plus 4 squared plus 3 plus 2 times 2 times 3 plus 4 to the 1 times 1. Let's see, that's 49 plus 5 times 2 times 7 gives me 119. What would be the units here? Well, the derivative of velocity would be inches per minute, or inches per minute squared. Based on these values, describe the speed. So we're heading to the right at a positive acceleration. So since v of 3 is positive and v prime of 3, which means acceleration at 3 is positive, the speed is increasing at time 3. On what interval, plural could be, is the particle moving to the left and the right? Okay, so let's think about our velocity. This is the derivative of position. If velocity is positive, we're moving right. If it's negative, we're moving left. So I would find it very helpful to figure out when it's at 0. When would this velocity be 0? Well, that happens when t is negative 2 and when t is negative 4. But it told us at the beginning that we're talking about time is greater than or equal to 0. So if I'm thinking about the number line, it's starting at t equals 0, and our number line would be going this way as far as time. So negative 2 and negative 4 are on the other side, so velocity is not going to be 0 anywhere in this interval. So I just need to pick a value. How about 3? What was it at 3? Well, we already had done that. Positive. We know it was positive right then. So since time is greater than or equal to 0, velocity is always positive. So the particle is always moving to the right.